I actually truly believe A/B testing is going through a renaissance right now. It is becoming widely adopted in product development more and more, and I'm sure most folks in this room have had some experience with A/B testing. And the one thing is when you're actually running A/B tests, you will know immediately, it just feels powerful, like you're actually looking at causal data. But if you've been working in it long enough and you're a wide variety of different situations, industries, you'll actually find that you'll hit some of the limitations of A/B testing. Or alternatively, you might be really getting a lot out of it and you just want to know, like, how do I take it to the next level? So that was really the inspiration behind my talk. I feel like a lot of folks talk about like the basics, but I want to cover some of the more advanced topics. My name is Tim. I lead data at Statsig, as you've heard. I did do experimentation while I was in the biotech industry. That was my small data. Then I went to Facebook, where I did experimentation on billions of users. And then I went to Facebook Reality Labs, where back down to a smaller amount of users. So I've seen it all across the board. And right now, I currently support our wide variety of Statsig's customers and their experimentation ambitions. And so I get a lot of experience with different industries and scales. Where's the point?
So point it,
There you go.
Yeah.
All right, I'll point it somewhere around here.
It's this thing, so just.
Okay, gotcha. Awesome. So Statsig was founded, I'll just talk a little bit about Statsig, just because we're fairly new. We were founded just 3 years ago. We fancy ourselves as a scrappy company, but we're growing and we're based out of the beautiful Pacific Northwest. There's two distinguishing traits I'd like to cover when we talk about Statsig. We're famous for a 100% in-office culture, so that's 5 days a week. We're also a very dog-friendly office. So I am sitting in the front row, and that's my dog Parker, who lucked out, who came on to work on photo day. Statsig is an experimentation and feature flagging platform that powers like fast growth companies that you might know, such as Notion and Figma. I believe Figma is the one giving the AI talk right now. But we also power enterprise companies like Atlassian, and also AI companies like OpenAI and Anthropic are two of our big AI companies, obviously. We help teams manage their feature rollouts, set up experiments, and provide results. In general, we try to make it as easy to become data-driven. We have two core products. One is Statsig Cloud. This is the one that's been around from the start. We're currently processing 600 billion raw events a day that are going into experiments for hundreds of customers. We're currently running 20,000 experiments simultaneously across more than 1 billion unique user identifiers. We have Statsig Warehouse Native, which is where you get the full power of Statsig Cloud, but the compute happens within your data warehouse. So the raw data never leaves, and yet you still get everything that I'm going to talk about. In this talk, I'll review some of what is A/B testing and just get down to the basics so we're all on the same page, and sort of my perspective on what are best practices and why it's the foundation for a data-driven culture. And then I'll get to the fun stuff. This is Experimentation 201 and some of the more advanced topics that we've had the pleasure to kind of start exploring. But why even A/B test? Well, there are many tools in the product analytics toolbox, but most of them are really correlation-based analyses. You're looking at data sets, you're trying to find trends, you're trying to find opportunities, but you're always sort of making a leap between causation and correlation. Experimentation, however, is a direct measure of causation. It is the basis of the scientific method and the gold standard for causality. And this is where decision-making, data-driven decision-making starts, in my opinion. It's like if we do A, we know B will happen, and roughly X%. Data has the power of trumping opinions, but you have to get started first. We encounter a lot of skeptics of A/B testing. They'll criticize it requires a lot of effort, it requires a lot of time, and we don't need A/B testing. We hire smart people. We hire people with great business sense, people with great product sense, people who've built successful products before. So we don't need to be trying random ideas and testing. But the truth is, among even the top tech companies, only about 1/3 of all ideas actually work. And this has been published data and research. And it turns out our intuition is often wrong. Does that mean we don't know what we're doing? No. The best baseball players hit a batting average over 300. This is because building products is just fundamentally hard. This is not easy things to do. But even if your intuition is good, experimentation still lets you quantify that impact and also allows you to dive in and produce richer insights. And if you are still not convinced, I recommend talking to Sean Taylor, who I believe is here at Data Council. He has this tweet, which is one of my favorites. It's everyone's running experiments, but only some of them have control groups and randomization. So if you are making changes to your products, which presumably you are, and you're not looking at your metrics, you're just really running an experiment without an analysis and already a predetermined conclusion. If you're at least looking at metrics on a dashboard, you're one step better, but you're missing out on that exquisite statistical precision that a control group will give you. So here's how A/B testing works, just so we're on the same page. You have a heterogeneous population of users, and the first thing you do is you're going to randomize those users into two groups. Randomization here really is the secret sauce. With enough users, you'll produce two equal-sized and comparable groups. For example, if 10% of your population are power users, half of those will be in the test group, half will be in the control group, about. But it will also control for other traits, such as Android, iOS, what percentage of new users will split by genders. And the really cool thing is that it won't just control for the known variables, it'll control for the unknown variables. So for example, let's say you are a lunchtime catering service. If 5% of your users had one of those delicious burritos for breakfast in the morning, we're going to split those equally too. So it'll control for that effect as well. With these two equal groups, we then subject one of them to a treatment and the other one to a control. We monitor this over the same period so that we can correct for seasonal effects. And then we usually read out some metric and look at that difference between the test and control. Any differences that we observe, because we've controlled for so much, we can safely attribute to the difference in the treatment experience. This is causality, and this is really the basis for just how A/B testing works and why it works. Now, in my experiences, there's a lot of ways to do experimentation wrong, and this is just some of my favorites. This is by no means an exhaustive list, but just generally a list of things I've learned to watch out for and recommend folks watch out for. First, you should always start with a hypothesis. You should know what, and it's not that hard. It's not, you don't have to deep dive into the science and get all wrapped up into the null hypothesis. It's just, what are you changing? And what do you expect to happen? It's as simple as that. And then I would focus on the primary effect. What is the first observable thing you expect to change? If you don't even see that, there's no point in looking at any other metrics further. So for example, if you shorten your sign-up flow, you're probably trying to make more sign-ups happen. So you should at least see that. But I would also ask yourself, what else do you expect to happen? Do you expect users to spend more time spent? Do you expect them to do more invites? And also, what could go wrong? And what are some of the metrics your business partners care about? The ones that might get some attention and we're actually delivering value to the rolling up to the top line business objectives. Next thing I recommend is always run a power analysis. This one people often skip. But it's basically it lets you estimate how many users to detect the result that you expect. This ensures your experiment has a reasonable chance of success. It'll guide you how many users and for how long will you need to run this for. I also recommend standardizing the methodology across your entire experimentation program. You'll want to use the same stats, the same metrics, the same decision-making rules. And the reason why is it ensures that the results you get reported from Team A and Team B are comparable. If somebody's claiming a 5% lift to retention, another team is comparing 3% lift to retention, I hope that's the same retention metric we're talking about. I'm also a big fan of using a 95% confidence intervals by default. There are certainly good reasons to increase and decrease that threshold, but unless you're able to clearly articulate those reasons before running an experiment, I would stick with 95%. It's a really practical and pragmatic default. It makes achieving a successful result attainable while maintaining a reasonably low false positive rate. And lastly, I wouldn't fret about interaction effects. Usually when folks are going on their experimentation journey, they'll start at one experiment at a time, then they'll want to double it. Then they start worrying about, well, what happens if those two experiments collide? There is a decent amount of research that says interaction effects are fairly rare, and when they are observed, it wouldn't necessarily change your decision that you make in the end. And what I find is that to eliminate interaction effects, folks go through a lot of hoops. They'll actually split up their user population, say half of you go into this test, the other half go into that test. Or they'll stagger their experiments and run them sequentially. This is actually pretty toxic to an experimentation program because it slows down your pace of innovation and prevents the number of it slows down the number of ideas that you can test. I will introduce you to a new character. This is the hippo. The hippo is short for the highest paid person's opinion. And it's how many businesses, certainly 10 years ago, made decisions. It's what you do when you are not data-driven. I've learned that experimentation is great for producing concrete and simple facts. For example, hey, this feature we know increases retention by 2%. Or this recommendation model hurts revenue by 1%. It's hard to ignore statements like these because they're causal statements. And this helps companies become grounded in data. I will talk a lot later in this presentation about fancy statistics, but I do encourage people not to get distracted. It's far more important to focus on culture rather than the fancy stats. The focus should be on the people and the processes. Sometimes I know as data people that's hard to swallow because we feel like we're experts in data, but people and processes matter a lot more to making experimentation work well. It should be trivial for an engineer to set up, execute, and analyze an experiment. Experimentation should also be a team sport. It should be PMs, engineers, and data scientists involved. Experimentation review is a critical part of a company's data culture. The scientific method was designed to invite questioning. And this is where discussions can take place, assumptions are challenged, where knowledge and best practices are shared to many people. And finally, your company should be optimizing for velocity. You should be finding ways everywhere to remove friction so that more ideas are tested. All right, with that covered, let's get to the fun stuff. Welcome to Experimentation 201. I'll share with you some of the limitations that some people encounter when they do A/B testing and the methods that are currently being used to address them. First one is pretty obvious. It's that experiments can sometimes take too long to run. And this is because variance can be fairly large. But variance in an experiment isn't purely random. It can come from many different sources. User-level variance can come from many pre-existing predictors. For example, imagine you are a car dealership and you're tracking purchase amounts. You may have cars on the low end with maybe like a $1,000 used car. You may be selling cars on the high end, such as a $100,000 sports car. That's a pretty wide range. That's a lot of variability and makes that metric, purchase amount, really hard to keep track of statistically. But what if we knew the price of the car that the user currently owns and do a correction factor on that? Somebody who's driving a used car is probably more likely to buy a used car. Somebody who's driving a new fancy car is going to probably buy a new fancy car. In 2013, a team from Microsoft introduced Cupid, which is short for Controlled Experiment using pre-experimental data. And this was truly a landmark paper, and most of the advanced experimentation platforms are using Cupid today. The Microsoft paper details a regression technique for adjusting user-level metrics based on pre-experimental information. And we, Statsig, have seen this reduce confidence intervals from anywhere from 30 to 60% across a wide variety of metrics for most of our customers. This results in faster experiments, lower sample sizes, and more precision on your results. This does have one obvious limitation, though, and it's that it's less effective for new users who don't have that pre-experimental data. The next challenge, it's sometimes called the winner's curse. And this is where the winners in A/B testing, the ones that you end up shipping, don't live up to the hype. It's pretty common, and I'm going to go over a bunch of reasons why it happens. The most egregious form of this, as we've seen, is we've had a customer whose old experimentation platform told them that over the course of the last 6 months, all of their wins that they shipped, it was plus 40% on revenue if you added them all up. That's wonderful, right? But the problem is, the CEO looks at the dashboard and says, our revenue last year was only up 5%. This is a great way to lose trust in your experimentation tooling, and which is one reason why they were looking to throw theirs out. There are several reasons this might happen. The first one is kind of unavoidable, and that it's whether the effects you're looking at are sustainable in the long term. Are the metrics you're seeing going to hold up, or are you just looking at novelty effects? The answer here is to run the experiment longer or wait for metrics to stabilize, but we don't always have that opportunity in time. The next is underpowered experiments. If you're short on users and time, you may be tempted to underpower your experiments. This can lead to a large amount of statistical error in your lift estimates. In this chart that I've shown, the null hypothesis is in black. If your treatment is no different than your control, you will pull from this distribution. We purposely set our threshold in experimentation at 95%, which is where the green shading starts. Any result we get that's on the right side of that green shading, we consider that a win, and we ship it. Anything left of that, we basically say that we cannot disprove the null hypothesis. If you have a good experiment, which is what the area in green is from, and the one I've shown here, the actual effect is clearly in the green zone. So this one is one that should be a good one to ship. But the way it works is that we will actually randomly sample from that green area, and the actual weight of the results you get is the average time. You're probably going to be a little bit to the right here. And so already the result that you get is probably going to be an overestimate for the actual effect. That's if you run a good experiment. But what happens if you don't have any effect? And these are the false positives. There's a 5% chance of still getting a result that's going to look good, even though it isn't. The next one is overestimation. And these are all flavors of the same thing. But if your experiment is good, such as in the orange, but it's not truly above the threshold, there's still a pretty good chance. In this case, the shading looks like it's about 30 or 40% a chance. There's still a pretty reasonable chance of getting a statistically significant result and declaring a winner. It's not bad. You still have a win here, but you'll overestimate the actual effect. And the last is biased decision making. I have no slide for this really. Well, I do. It's this red area here. But the truth is, this is human error. This is when we look at results with rose-colored glasses and cherry-pick results. There's many ways that this can happen. And this, sometimes we're looking at results and they're clearly bad, but we have ways to sort of hand wave. Like, we had an outage in this metric for a day and a half. That's probably what messed this up. Or, hey, we had these other metrics that are positive. Like, it's okay that this one looks bad. And these are very one-sided. We're biased in declaring our victories, and so we tend to overestimate things that are actually bad. All of this does lose trust in experimentation when you're looking at results, and unfortunately can encourage people to game the system. The solution here is holdouts, which some of our larger customers are running now on a regular basis. A holdout is when you have a small subset of users that are intentionally withheld from a feature, even after you've done a full rollout. This is typically a longer term period, like 3 to 6 months, could be even a year. And there's many uses for holdouts here. You can do them as a team-wide, so basically whatever the team is in charge of and they're doing over the course of a half, you can sort of keep track of what the cumulative impact is. Next one is feature-specific, if you want to just hold out a feature or a set of related features. And the other one's hypothesis-based. If you have some core assumptions that your company has always sort of believed in, maybe it's time we could challenge that by actually running a long-term test on a small percentage of users. Holdouts are fairly powerful. One is that there's a huge amount of accuracy that you'll get by measuring an effect over a long period of time. A good example of this was Meta recently published some work on notifications. In the mobile app world, notifications are known as a pretty reliable tool and strategy for getting engagement on your app. Notifications always drive up engagement. You ping somebody a message, they're going to look at it. But what they found was that if you actually tighten the threshold on the quality of notifications you send, so we send less notifications, that in the short term, you do end up with less engagement. But after about 12 months, the interesting thing was that engagement level starts to come up about 6 months where it's about equal. And then in the long term, so 12 months, sending less notifications is actually better for engagement in the long term. This is the kind of data that you can get out of a holdout. The next one is really cumulative estimates. If you really want to measure that we've shipped 3 experiments last half, we want to make sure that they add up. You can actually put them in a holdout together and evaluate how good those wins really are. You can also evaluate as a team making the correct decisions in experimentation. One added advantage of a holdout is it's kind of a re-roll of the randomization process. If you've done a 50-50 test, maybe you've got it slightly biased to power users or something. The holdout will give you, for example, if you hold out 2% of users, basically a new draw on that. This holdouts can sometimes be used in performance reviews to evaluate how well a team is doing or whether they're meeting their goals. It can be used for resourcing if you want to double down on the teams that seem to be hitting everything on, all their ideas are working well. And also for just keeping teams honest in making their decisions. There is some downside risk. In fact, there's a lot of downside risk to running these. Holdouts are deceptively expensive. And the reason why is that the engineering teams actually have to maintain 2 branches of code. You've got to maintain the group that has all the features and the group that doesn't. And as hard as it is just to keep one branch up and running without any bugs, they now have to do 2, so it's double the work. And if you actually don't do it right, you'll contaminate the holdout. So for example, if your control group is not getting bug fixes, obviously they're going to perform worse, and that holdout data is not valuable anymore. So my advice for around this is holdouts, if you're going to pick that as a strategy, need to have top-level buy-in. So the leaders in your company should be like all bought in that this is something we want to invest in. The second thing is you should be reading out holdouts on a fixed cadence. So for example, every single month. This gives it visibility, but it also helps remind you that if you're not able to prove value from a holdout, you should question why you're doing it. All right, let's talk about the peaking problem. Standard hypothesis test is based on stats that generates a 5% false positive rate. This is usually based on a single observation at the end of your experiment. The problem is we've been telling PMs and engineers to be monitoring your product dashboards continuously. And so when they launch an experiment, they want to know exactly what's happening now. And just monitoring how your experiments are doing is just human nature. Unfortunately, this does mess up with the stats, but there are plenty of good reasons why you may want to look at results early. First is, maybe you found a win and you want to ship that because if your revenues are up 2% or if your users have been, are engaging with a product that they love, you just want to get that to everybody right away. Second one is detecting regressions and being able to abort experiments. Hey, this is a really bad user experience. We're crashing a bunch of devices everywhere. We need to get this out. So you rather detect that now than at the end of the experiment. But there are some practical considerations when deciding how to handle the peaking problem that makes the statistics really hard. For example, how often are people going to peak? What's the frequency? I can tell you just looking at Statsig data, people are less likely to look at results on a Saturday and Sunday. But that's important to know in the stats, is how often is someone looking. And when they look, are they willing to make a decision? That's really unclear because sometimes it could be which results are up, which results are down. What is their decision-making threshold? And it's hard to really clearly articulate that at times. There's also times you'll want to make sure, most people want to optimize for long-term effects. And so you don't want to really trigger some alarm just because we're looking at novelty effects in the early days. The solution here is just generically called sequential testing. It's a generic term for any statistical method that accounts for continuous or periodic monitoring. And there are many of them. All of them pose trade-offs between things like sensitivity, speed, and statistical power. We evaluated a bunch of sequential testing methods, and we ended up selecting one called MSPRT, which is short for Mixture Statistical Probability Ratio Test. We evaluated this. The nice thing about Statsig, we're able to evaluate this across hundreds of different experiments and thousands of different metrics. This covers everything from retention to revenue to engagement rates. And what we found was that in general, that this MSPRT lets you detect 60% of your wins when you're only halfway through an experiment, which is pretty good. It has the added advantage of not requiring a tuning parameter as well, so it works very generically out of the box. There is a human problem here, as there is in most of the things I will talk about in this talk. Let's say you have a new ranking model, and you're generating a ton of clicks. And sequential testing, even after you've applied the statistical correction, says that this is statistically significant. This is good. We definitely know there's more clicks from this ranking model. So should you ship this early? What if I tell you that you have a guardrail metric? You might be Amazon, and there's a rule that you're not allowed to ship any experiments that are negative to revenue. So you go and take a look at your revenue metric in this experiment, and keep in mind we're only 2 days in, and you find out that it's between -2% and +2%. Is that okay? Probably not, because it includes negative margin in there that could be pretty significant to your business. So our recommendation is now shifted to that you should use sequential testing to identify regressions that are worthy of aborting. But if you want to ship the experiment, because it's a good experience, you should really wait for the full duration, so that way you can fully evaluate all your metrics. You'll get the maximum statistical power at that point to be able to evaluate that revenue guardrail. I personally really like this model because it kind of flows with human nature. We tend to be rooting for experiments. We want them to succeed. And what we've done with this framework is we've given you permission to abort early, which is not really something you want to do unless you see a result that's clearly bad. But if you want to have the win and book it in, you have to wait for the full experiment. Now let's talk about randomization. Is everyone here familiar with Canadian money? It's a lot like US money, but there's some extra coins. There is a $1 coin, which is this kind of golden one here. We call that a loonie. And then the big bimetallic coin, which is really cool because it's made of 2 different metals, is called the toonie because it's worth $2. And technically the penny is no longer, but I've kept it here just for convenience in this example. If I take a pile of Canadian coins, this pile here, and I randomly split it into 2 groups, I will very likely end up with an imbalance as shown here. This pile is $5.78. The other pile is only $2.32. Why is that? Well, it's that some coins are worth orders of magnitude more than other coins. The $2 coin is 200 times more than the penny. And in such a situation, randomization fails. There's 2 $2 coins in this pile. That's $4. That's a pretty significant chunk of the total value. And there's a 50% chance that those 2 will end up in the same group. So this is just an inherent problem in randomization when you have these factors at play. Instead, what if we carefully balance the 2 groups? We carefully counted all the $2 coins and split them, the $1, so on and so on. We can generate 2 equivalent groups that are now comparable, and this is what we want. You may be asking, well, nobody else does this. Why is this important? Well, the truth is this is actually a real problem for B2B companies. And 1/3 of customers on Statsig are actually B2B, which means that they don't do user-level testing. They do company-level testing. If you are a company like Notion, it doesn't make sense to give half the users in a company a special feature and the other half not. So B2B is prone to this problem because they suffer from 2 problems. One is small sample sizes. Instead of millions of users, they probably have thousands of companies at best. They also have a humongous skew in their data. Example is if you are Stripe, your customer base, which are companies, is everything from your mom and pop coffee shop that has Stripe enabled at their little location, or you could have companies like Walmart and Amazon, which are enterprise scale. This is what I mean by orders of magnitude difference. And what happens if Walmart and Amazon end up in a test group together? It's going to cause major imbalances. So they can apply stratified sampling. This is easier said than done, but it can be done, and there's many ways to do it. The nice thing about once you have this stratified is that not only is your 2 groups on average balanced, but you can actually start diving into the strata. So you can understand the impact of your experiment on the big enterprise customers to the medium-sized ones, to the small ones, because you may want to understand the trade-offs and make sure that everybody is kind of benefiting from your changes. All right, network effects. Network effects can be a big problem depending on your type of business. This is where your test and control group can actually interfere and affect each other. This violates a key assumption in experimentation, which is that every unit you're testing on is independent. This is most commonly found in businesses that have a two-sided marketplace. So this could be social networks. This could be online marketplaces like eBay. This could also be communication platforms. One industry that has actually pioneered how to solve network effects well has been the ride-sharing industry, so Lyft and Uber. What the problem they kept running into was they would test new algorithms for rider matching or driver matching. And what it can do is that if the test group suddenly starts matching more often with drivers, the driver supply goes down, and the control group now finds it harder to get rides. And so when you're trying to measure how the test group is engaging and how the control group is engaging, your estimates now are a little bit biased and skewed. And it's not really a clear indication of what happens if you were to ship this algorithm to 100%. You're not able to generate a reliable estimate. Switchback tests are what they came up to solve this problem. So in the top part, instead of splitting your test into your group into test and control and monitoring them over a period of time, we're now going to split on time buckets. So in this case, I have 8 a.m., 9 a.m., 10 a.m. Shown here. The entire ecosystem gets the treatment effect applied or pulled back. And you can let it stabilize and be able to measure the metrics in this that you care about. I think I'm also a believer that this kind of testing is going to work well on infrastructure experiments on the back end, because you usually have all sorts of network effects where nodes are talking to each other and actually affecting each other as well. Picking your time interval is very critical here. You want to have enough switches because that's your sample size and the number of observations you get. But you want a time interval that's long enough that allows you to measure the ecosystem and get some metrics that you trust, and it's not just an artifact of the switch itself. Another limitation, typically when you run an A/B test, for example, a 50-50 test, you'll keep that 50-50 split for the entire duration. This is what keeps the two groups comparable. But what if one of your groups is doing well and you just have a good hunch? Do you want to shift your traffic? In some cases, you do. In cases where time is in really short supply. For example, you are a retailer and it is Black Friday and you have a test going out testing a Black Friday deal. Well, do you really want to wait a week to ship this experiment? Or would you rather ship it in the next hour or even within minutes if one starts to look a little positive? One solution is multi-arm bandits. Or this is actually probably the most common solution for this problem. Let's say you're a news website and you're showing a sports score, and you want to test like 8 different video thumbnails and maybe a bunch of headlines as well. But you don't know really which one is going to be best. You generally want to converge on the best variant as quickly as possible because scores get really old. You don't want to find the optimum headline and thumbnail a week later. Because people want to look at that. You want to get those clicks now. This example is great because the one thing that multi-arm bandits do really well is they will automatically allocate traffic. They'll actually dynamically do so without manual intervention. You don't really want to grab a group of 4 data scientists to look at every single thumbnail and results and make a decision. You just want this to happen automatically. And it will also let you test a ton of variants. So if you have 8 different variants, multi-arm bandits may take a while to find the winner, but they're actually really great at throwing out the losers. So you may start off with 8, but it'll quickly dwindle down to 2 or 3. One major downside, though, is that this isn't great for producing learnings. You don't get to draw inferences that are applicable for future tests. And it's also not good for situations where the decision-making is sometimes nuanced and complicated. For example, trade-offs between metrics. Finally, let's talk about heterogeneous effects. In A/B testing, we usually measure the average treatment effect, but as you know, there's no such thing as an average user. A major software company, which I'll keep their name anonymous, because they told me this in confidence. They ran a sign-up flow test. In fact, their team was in charge of improving the sign-up flow. And they would find a test, for example, like this example here, where you may find a plus 0.4% lift. That's great, right? But when they looked into it and split it by gender, they actually found out that it wasn't the same. That men were getting a 0.8% lift, and women were having a minus 0.2% lift. It's still positive, so you probably want to ship this experiment. But the problem became when they looked at the past 10 experiments, and they were all like this. And so what they were ending up with was they were shipping a bunch of features that were all biased in the same direction to the same gender. And at the same time, leadership was asking, why is our user base 70-30 men, women? So they decided that like, this information was pretty important. The split was critical for changing the ideas that they were going to test in order to address like a top-level objective. This area is probably pretty common for folks, but you need to be able to split this data. What is the most common thing is finding bugs. So you can have a revenue win on a product change that might be like 2%. That's great. But what if you found out that there was a bunch of Android devices that had small screens that you didn't really test the UI on, where it was completely broken? You go back, you fix that bug, and now your win is up to 3%. To do this right, you usually have to run automated detection across a whole set of attributes, looking for that, and you'll want to run corrections for type 1 error rates due to the multiple comparison problem. This is experimental meta-analysis. This is not something which I'm by any means an expert on, but something we're looking at now. A lot of our customers have run dozens, if not hundreds, of experiments now, and we have a really cool data set of a bunch of experiments that have been tried and a bunch of metrics. This feels like something that's really powerful. You're not just looking at observational data. This is somewhat related to causation. And it's an area that we're sort of exploring at the moment, and we don't have all the answers. Some ideas of things I could think of to do with this. I think if folks were here at yesterday's Brent Cohn's talk, he talked about just drawing a line, which is what I've drawn here. And this really helps you understand the relationship between metrics in this data set. Maybe you can help identify proxy metrics. If you know that some metrics take 2 weeks to appear, maybe there's a proxy metric you can rely on that's correlated. This also helps you understand in general whether some metrics move and whether some don't. For example, is it reasonable to think that you will drive time spent up by 5% in an experiment? I don't know, but let's go and take a look historically what has been possible. I did a whirlwind tour through a bunch of solutions to a bunch of cool problems in testing. One takeaway you could get from this is that there is a lot you can do and a lot of cool stuff that people have come up with for solutions. But I do want to leave you with one lasting thought. While these are neat, and I definitely love working on them, stats engines don't build culture. I don't want folks to overthink experimentation. To me, it's always better to run an experiment than to talk yourself out of the problems that experiment might have and not run it in the first place. This concludes my talk.